Let us have a look at ANOVA now. We basically need two sets of data, and to analyze the variance, we now select the two data columns along with their headers. Go in Data, Data Analysis, and ANOVA, single factor in this case. Our input range is here. These are grouped by columns, of course. There are labels in the first row. And alpha, let us keep it as 0.05. And let us give it its output range here. This is the full analysis of variance of the given data. Let us quickly move to hypothesis testing as well now. This is the most basic sort of hypothesis testing. We take two groups of data and compare their means, their averages with each other. Our hypothesis, our previous assumption, is that both have no difference in their means. They are very similar means. But we must reject that hypothesis, that null hypothesis, if there is a significant difference. Let us see how this can be used. We have calculated the variance here by making it a table. This will help us further. So to start with, we go in data analysis again. We move down here, z-test, two samples for means. This is our variable 1. This is our variable 2 with label. Yes, we have the labels here, we take this. Now the mean difference will be 0 as per our null hypothesis. We assume there is no great difference. But we will tolerate some difference, which is shown by alpha here. Level of significance here is 0.05. Now the variance of variable 1, we know it here, 29197751. Variance of variable 2 here is 36238064. This is the result of this z-test. In these 12 observations, this was the hypothesized mean. This is the critical z. Here is the result. This is the z value, the test statistic obtained here. And the critical value is 1.95. Since either side's variation will reject our null hypothesis, we take two tail, or else we'll take one tail. So either side here, the z should not vary more than 1.95 in magnitude, and 1.62 is less than 1.95. So we accept our null hypothesis. Let us see another case here. This is a sample, and we are assuming mean age is 23. Now, does it significantly differ from it? We have been given standard deviation of this is 5, alpha is 0.1. These will be given in the question. So assuming this as the data, we will first consider the mean is 23, and our alternative is that it does not equal 23. It is significantly different. Now we list the data again. You may have noticed there is only one z-test option in data analysis, and we need two sets of data for it. Hence, though we have only one column, we'll have to make a dummy. Here is our dummy column. Let us see how to apply z-test now. Just this option, two sample for means. Now our variable 1 is here. Variable 2, we don't actually need it, so we are putting a dummy here. The hypothesized mean is 23. This talks about difference, but we don't have a difference here. We directly write the mean 23. The variance of this variable age has been given as 5 in the question, and we keep it minimal for the dummy so that it does not affect our calculation. Let us make alpha 0.01 here. We are not tolerating big variations now. And the output range is now here. We can now remove this and this as well. What we are concerned with is this value of z, which is much bigger than the critical value. Again, we are talking about both sides variation. It shouldn't be much less than 23 or more than it either. So we can see that there is a large variation and our null hypothesis will be rejected here. Test statistic is greater than the critical value. We will now see the application of solver for linear programming problems. This is how a question will look. We have limited resources and we have to maximize profit or else minimize costs. So let us see here. We have 200 hours on machine 1 and 400 on machine 2. These can make two things, chair and tables. But the contribution from chair is rupees 30 and from table is 40. So how can I maximize contribution here? We must find the optimal mix of production. That is, how many chairs and how many tables should we produce to get the maximum contribution? The question will also have this. This table shows that M1 takes 7 hours to make a table and 4 to make a chair. M2 takes 5 to make each. What we want is the mix of production, units of chairs, units of tables, and of course the maximum contribution that we can get. We want all these details. So we start with this. We want to maximize the contribution. So let us make a cell here showing maximum contribution. But this has a formula behind it. Number of chairs into contribution from each chair plus number of tables into contribution from each table. That is exactly what this formula shows. Tables into contribution from each plus chairs into contribution from each chair is equal to the total contribution. We are multiplying and adding the contributions. So we have a complete formula here with the contribution and table chairs given. These two start with 0, of course. But we must also consider the constraints. We saw the objective here. The next is the constraints. As given in the question, we can see we have these constraints. M1 takes 7 with table, 4 with chair. And the constraint is its maximum capacity 200. It does not have more than 200 hours. And each takes this many hours. So we have the hours required for each, and we know that it has to stay within this in total. Hence we apply that table here and also mention the max capacity. Another constraint is that we have to make at least 0 chairs and 0 tables. That is non-negativity.
The totals can be found by the time taken by the machine to produce a unit into the total number of units that we get at the end. That will give the total hours that are spent, which must be under the constraint.
We will now go to data, solver. Now we need the objectives here. The objective is shown here. We want to maximize the profit, the contribution. But what cells can we change in order to maximize this? We can only change the number of tables and the number of chairs as well. So let us select both. Now we must add the constraints. The total number of hours on machine M1 is less than its constraint, that is the maximum capacity. What is the total? We click here. This is smaller than equal to. The constraint is right here. We add this. Next, the total on this is less than this constraint. These are our two constraints. Here non-negativity is already being chosen. We are using a simplex LP method and we will solve this now. 50 chairs and no tables. This combination will get us the maximum contribution.